It's my pleasure to be here today, and today I'm going to talk about some recent results that Paul Beam and Paris Coutris and myself have obtained at the University of Washington about a very fundamental question. When you want to compute a query on a large data set, how much communication do you need to pay in order to compute this query on a large number of servers? So that's the setting of my talk. We want to do big data processing on distributed servers. If you want to think about concrete examples, general programs, you would write them in MapReduce or maybe Spark. I'm especially interested in declarative queries, so like SQL queries or relational algebra queries like Big Latin or Google's BigQuery. Or Shark, or the system we built at the University of Washington called Myria, which supports general relational queries with recursion. And the question I want to ask is, how can we reduce the cost of processing these queries on distributed clusters? Now, these queries are traditional database queries, but the focus of traditional database engines has been on the I/O complexity, because this is where most of the performance loss went in getting the data from disk. When we do big data processing with a large number of clusters, the reason why we use many servers is to have enough main memory to fit the data in main memory. So therefore, the main bottleneck is no longer the I/O cost. Once the data is in main memory, then the main bottleneck is the communication cost. How do you distribute the data, make it available to all the servers? So this is the problem I'm going to discuss in this talk. We have a number of servers P, and we have a problem that we want to solve. And the question is, how much communication do you need to pay in order to solve this problem? I should warn you, this is a theory talk. I'm not going to show you fancy slides. I'm going to show you lots of formulas. But I think it's an interesting theory that is relevant to anyone who is interested in processing large data sets. Now, the kind of problems that I'd like to analyze today are going to be queries, database queries, actually quite narrow class of queries, namely what we call full conjunctive queries. Think about them as select star from where. SQL queries of the form select star from where. No duplicate elimination, no distinct. But the same problems, the same questions that I'm addressing today, they also apply to more general problems like machine learning problems or matrix problems or linear algebra. And I should also make some advertisement. Some of the techniques are actually implemented in the Myria system, and Bill Howe is going to talk about them early this afternoon. So in order to establish how much communication is needed, we need to talk about theoretical models of communication. Now, the early models of parallel processing, of parallel computation, they combine the communication and computation cost. For example, the early PRAM models or the circuit models, they don't talk about communication. They talk about amount of memory. And a more recent model for MapReduce by Karlov and others essentially borrows the same principle. Explicit model of communications, interestingly, they have been designed in particular for studying the I/O cost. The earliest model by Hong and Kung, which is very well known, is the red blue pebble game, measures how much I/O you need to, how much communication do you have to pay from disk to main memory. More recent models that we are interested in were developed by Das Sarma and Ullman and Afrati. But this talk today is going to be focused on a very simple model of communication that we developed that's published in 2 papers in POTS 2013 and 2014. Good. So here is the outline for my talk. I'm going to describe to you this very simple model of communication that we call the massively parallel communication model. Then I'm going to show you how to analyze the communication cost for a simple but interesting query, the triangle query. Then I'm going to generalize this to arbitrary full conjunctive queries, and then I'll have a short discussion. Okay, so here is a massively parallel model of communication. We have some input data, and the size is m bits. It's not n. I apologize for this. We reserve, think about a graph. So n would be the number of nodes, but I'm measuring the number of edges. So the size of the data is m. It's capitalized because we measure it in bits. This is the size of the data. And we want to process the data on P servers. And initially, the data is distributed uniformly on these P servers, and the communication proceeds in round. In every round, the servers, they do some local processing, and then they reshuffle the data. That's the communication. And you can do this repeatedly, and an algorithm is a sequence of such rounds. Now, when they exchange the data, I'm going to denote L, the maximum amount of bits received by any server. So the total amount of communication is P times L. But L is at most P times L. So L is the complexity I want to study. Ideally, I would like to have L m by P. I would like essentially every server to receive only a P fraction of the amount of data during each communication round. This is kind of difficult to achieve if you want to reduce the number of rounds. So some problems, you can solve them if you allow a replication factor, which is a power of P, P to the power epsilon. We call that epsilon the space exponent. We would like to have epsilon 0, no replication at all. We definitely do not want to have epsilon equals 1. If epsilon is 1, then you essentially are allowing the algorithm to send the entire data to every server, and that is degenerate from our perspective. There is then no parallelism going on. So notice we do not impose any restriction on the power of computation of the servers. They have unlimited memory, they have unlimited processing power, they can even compute undecidable problems. We only focus on how much communication do we need for this problem. Let me show you a simple example with a bread and butter problem in database processing, which is computing the join of two relations. So R of x and y, think of it as a table, has attributes x, y. S has attributes y and z. We want to compute their join. So initially, the data is partitioned on the P servers. Maybe half of them store the relation R, half of them store the relation S, or maybe they're partitioned some otherwise. And the standard way to compute a join is in one round. And it's a hash join, where we redistribute the data by hashing it on the y attribute. So every server that has a record R sends it to the processor, to the server, whose number is a hash function applied to y modulo p. And every server that has an S sends it to h of y. So in the last step, every server computes the join locally, and they output the result. Very simple. So this is the bread and butter of today's parallel database engines. Everybody implements a join this way. And the load in our model is, the ideal one is m by p, assuming that there is no skew. So what is skew? In this context, well, imagine that you need to partition every relation into p buckets. And you're using the value y to do this partitioning. Now, if one value y appears more than m by p times, then of course that bucket will be overloaded. So the threshold, we can only tolerate, we can only run this algorithm with this load if every y has a degree at most m by p. Okay, and the space exponent here is 0. Very simple. This is how database engines, parallel database engines work today. This is why people say that SQL is embarrassingly parallel, because it's so easy to compute. But we want to ask the question, what is this communication load for more complicated queries? In particular, two questions are of interest, but I will only have time to discuss one. The first question is, what if we restrict to a single round? What is the minimum and maximum communication load per server that we need to pay in order to compute a given query in one round? My talk today is going to be about this problem. A second problem is of great interest. What if we fix the amount of communication load that we're willing to pay per round? Then the question is, how many rounds do we need in order to compute the query? This turns out to be a much harder question. We only have some partial answers, and I'm not going to discuss it today. Good. So let me start with the first, one example of how to analyze the communication cost for a query that is a favorite for people who do who implement massively distributed query processing engines, which is computing all triangles in a data set. So here is the query. We are given three input relations, R, S, and T, and we want to find all triangles, all triples x, y, z, such that x, y is in R, and y, z is in S, and z, x is in T. The benchmark that everybody uses is a data set from Twitter, where the relation represents follows relationship. X follows y, and now you want to find all triangles where x follows y, y follows z, and z follows x. Okay, so how can we compute this query? Easy. All database engines do it in two steps. First, they compute the join of R and S, and we know how to compute the join. We partition we hash partition on Y. And in the second round, they take this temporary table and they join it with T, and it's the same join. There is a big problem with this approach, and all database engines have this problem. They can't essentially compute this query on a large data set, and the reason is because this temporary table that you get after step one is way bigger than the size of your result. The temporary table contains all triples where x follows y follows z, but only a tiny fraction closes the triangle, and z also follows x. So we tried this, and for the data sets we experimented with, we simply couldn't run it on 64 servers. Good. Let me show you now, and this is perhaps the most fun thing you should take out of this talk, is this algorithm. It's a very smart algorithm for computing this query in a single round. And it was discovered by several people, but the best description is by Afrati and Ullman from 2010, EDBT 2010, who described it in the context of MapReduce. Here is the algorithm. Take your P servers and take the number P and write it as a product of three numbers, P to the 1/3, each of them. That means that you are organizing your P servers in a cube of size P to the 1/3. So every server now is identified by three numbers, I, j, k, between 1 and P to the 1/3. Okay. So now here is what we do in a single round. Every server who has some tuples from R will take those tuples and will apply the hash function on the x and y attribute. This gives us the two of the three coordinates where this tuple has to land in the space of servers. But it doesn't have the third coordinate. So because it doesn't have the third coordinate, it's going to replicate this tuple for all servers that have these two xy coordinates. Okay? So every record is going to be sent not to a single destination, but to p to the 1/3 destinations. During the same round, every tuple, every server who has S records will apply the same principle, will compute the y and z coordinate by applying a hash function, and will replicate this record across that dimension. And the same thing for the t tuples, and here is where my PowerPoint animation reached this end, so this is not so nice, but you can see what happens here. And we are done, because now every single potential triangle x, y, z is seen by the server whose address is h of x, h of y, and h of z. Beautiful algorithm. So let's discuss it. My claim is that the load of this algorithm is m by p to the power 2/3. Kind of easy to see because m by p would be the ideal, but we had to replicate each item p to the 1/3 times. So this is why p to the 1/3 exponent disappears. This is our replication. This is our space exponent. This is I've captured this in a theorem. The load of this algorithm is is m by p to the 1/3. Notice also that we can tolerate a slightly larger skew, because every value is sent to only p to the 1/3 buckets. So we can tolerate a degree up to m by p to the 1/3 from m by p, which was the heavy hitter degree for a simple join. And moreover, we don't have this big intermediate table. This works. It works actually much better than the two-step join. The question is, can we do even better? Now we got a taste for a smart algorithm. Can we improve this? And this is what we proved in a paper last year, that the answer is no. You cannot compute the triangle query in a single round with fewer with a smaller communication load. And here is the result. So let me denote. This is a formula. Given m, the size of the input data, and p, the number of servers, let me denote L lower to be this quantity, m by p to the 2/3. So the theorem is that any one-round deterministic algorithm for computing the query requires at least L lower bits of communication per server. Okay, we actually prove something stronger. We prove the following, that if you insist in running an algorithm that has a strictly lower communication load, then that algorithm is not capable of reporting all the answers. In fact, we characterize exactly how many answers that algorithm can retrieve. Namely, is a ratio of between its load and this lower bound to the power 3/2. Okay, so I have about 10 more minutes. 13, I think 13 minutes. So I'm not sure if I can. Yeah. Good. So I will probably skip the proof, but before I get here, let me make some comments. So what that means is that if you design an algorithm and want to impose a particular space exponent, which is less than the lower bound, which is 1/3, then your algorithm will report only a fraction, which is 1 by p to some complicated power here, of the correct answers. Now, to me, this is very interesting because this fraction decreases as the number of servers increases. This tells us that the model captures correctly the communication cost. The more parallelism you want, the harder it is to solve that problem. Parallelism makes it hard. It doesn't make it easy. It speeds up things when it works, but it's harder to use P servers the larger P is. The second observation is that we can't prove this theorem for a fixed input. It has to be over random choices of the inputs R, S, and T. Because for every fixed input, you can design a specialized algorithm that looks for this particular input and signals to all the servers that this is the special input, and if that's the one, then it can solve it very, very efficiently. So our statement is for a random choice of R, S, and T. And by our lemma, this algorithm also holds for randomized algorithm over a fixed input. One more discussion. In a recent paper, Ballard and Demel and others, they proved a quite interesting result about Strassen's matrix multiplication algorithm. So they used the old an extension of the old computation DAG model from '81, the red-blue pebble game. And they proved that in this model, any implementation of Strassen's matrix multiplication algorithm must have a communication load, which they denote I/O in this paper, given by that long formula. Don't look at that. Look at the red formula, which is a special case, which essentially is the size of the problem divided by a power of p. And the power of p, if you can't read it, is 2 by log of 7. The log of 7 because of Strassen's algorithm. This is very similar to our result in spirit, but there are two differences. On one hand, their result is stronger because there is no restriction on rounds. On the other hand, their result is weaker because it applies to a specific algorithm. It doesn't tell us it doesn't give a bound on the matrix multiplication problem, but on Strassen's algorithm for matrix multiplication. It's also restricted to the CDAC model as opposed to the more powerful bit model. Good. I'm going to skip the proof because I want to use the last few minutes to show you how to extend this formula to arbitrary queries. And this is a second cool idea that I'd like you to take from this talk. How to think about an inherent limitation of the communication cost that you need to pay to answer general SQL queries. Here is how a SQL query looks in a mathematical notation. So we have several relations, S1, S2, SL, and we join them. And they have fixed sizes. And we want to see what is the minimum communication cost that we need to pay. So to give an intuition, I'm going to start with a very simple query, which is a Cartesian product. How do we compute all pairs x, y, where x comes from S1 and y comes from S2? By the way, Jeff Allman has a paper in 2013 where he describes precisely this problem in the context of MapReduce, essentially showing how easy it is to program this in MapReduce the wrong way. Now, in the MPC model, it's easy to program in the right way because we know what we have to do. We have to decompose P into a product of two numbers, and then we distribute S1 to the first dimension and S2 to the second dimension, and then we just compute the Cartesian product locally. The question is, how do we choose these two dimensions? It's easy to see that we need to choose them proportionally to the sizes of S1 and S2. Okay, so I have a short proof here, but it's easy for you to derive it. But you can convince yourself that this is a lower bound. If M1 and M2 are the sizes of the two relations, then you must communicate so many bits. Every server must receive so many bits in order to compute the Cartesian product. Good. So here is now the really cool idea. Start with a general query. Has many joins. Select what's called an edge packing. This is a subset of the atoms that do not share any common variables. Okay, so this would be this set here. Consider the Cartesian product of these atoms. So I remove the other atoms. It's easy to convince yourself that any one-round algorithm that computes a query correctly must also compute this Cartesian product as a side effect. Because if it fails to gather any combination of values from this Cartesian product, because it doesn't see the other relations, it might fail to report the correct answer. So therefore, it's easy to notice that one lower bound is exactly the product of the sizes of the relations in the packing by p to the power 1 by the size of the packing. What we proved that this generalizes from integral edge packings to fractional edge packings. For every fractional edge packing, the lower bound, this formula here, which is essentially a weighted geometric mean of the sizes of the relations weighted by the fractional edge packing divided by p. This is a lower bound for any algorithm that computes this query. Since any fractional edge packing is a lower bound, takes a maximum, and that is also a lower bound for this query. Good. So I know I'm running out of time, so let me just go to discussions. So there are two extensions that I'd like to bring up that I didn't have time to address. One is multiple rounds are much harder. So we have some partial results, and this is kind of a call for arms to look at these kind of problems. What we discovered is that there is a connection, if we fix the communication cost, then there is a connection between the number of rounds and the diameter of the query. But we don't have matching upper-lower bounds yet. Also, the communication model is weaker. Apparently, it's much harder to extend these kind of results to the bit communication model. The second kind of extensions that we also barely addressed is how do you deal with skewed data? And that's something that's coming up in a paper in POTS next week. And finally, how do we analyze the communication cost for queries beyond conjunctive queries like matrix operations and machine learning? And that's wide open. Good. I will stop here. Thank you.